Okay, so I'm going to talk a little bit about propensity score matching today as a potential approach to program evaluation. So just what I'm going to try to get through today is the background and rationale for using propensity score matching, some methods. I'll go through kind of a general methods, and then I'll go through two different examples that apply the methods. And then we can talk about some of the benefits and drawbacks and hopefully have some discussion at the end. So I might fly through a few of the examples and just point out the key pieces so that we make sure we leave time for discussion, because I'd love to hear all your thoughts about it. But first I want to know who has applied propensity score methods, any propensity score methods before in their work? Just one? Okay. Sort of.
I had help, so I didn't do it myself, but I did the process.
Okay. Okay, so you've been tangentially involved in a okay. And how many of you know a little bit about what it's about? Show of hands. Okay, about half. Okay, great. Well, we're going to start kind of at the beginning here. This is the result of kind of a few years long process of me trying to figure out the literature and figure out the best way to apply these methods. So hopefully it's helpful to you. I am still learning, as I always am, so I'd love to hear your input. And as I've presented this in different places, we've thought a lot about these methods and revised them over time. So I'd love your input. So first of all, just for background and rationale, it's often not feasible or ethical, as we all know, to conduct a randomized controlled trial, right? So Pat was talking about quasi-experimental trials. So we're in that realm here with propensity score matching. So when we want to evaluate a program, selection bias can be quite an issue, right, when we're doing a quasi-experimental design. So everybody knows what selection bias is. Let's do a quick review. This is from the SCLO Epi textbook. So this is the bolded arrow here, but that's not the only way that selection bias can happen. So I just want to get you thinking about selection bias. If you're thinking about women getting into prenatal care, what is one example of potential selection bias if your outcome, if your exposure or your intervention is prenatal care or early prenatal care entry, right? Your outcome is some kind of birth outcome. What is one potential way that selection bias could be happening? So selection bias, right, is when your sample, your study sample, is not representative of the referent population and could lead to bias. So what's one example for early prenatal care? Which cell in the sample might get over or underrepresented? Right, so sample A may be overrepresented because of women who had a prior poor birth outcome and are motivated as soon as they know they're pregnant to get early prenatal care. And so how would that bias an estimate if you're looking at the relationship between early prenatal care and low birth weight? Which direction would this bias then? Here. If you have overrepresented people who are getting a good intervention who have poor outcomes, bias towards the null, right? What's another example of selection bias that could work in a different way for early prenatal care? Sorry.
Who are really healthy or really, concerned about their pregnancies, you're not going to get the people who are using alcohol and drugs.
Right, so here's me. Every time I get pregnant, I'm like calling up, I need my first prenatal care visit, like stat. And I've never, I've been very fortunate, had very healthy pregnancies. And, so I'm in the B cell, right? So that could be overrepresented. We're not quite sure where the selection bias is. I mean, there are lots of different possibilities in terms of selection bias with prenatal care. There's also the healthy unexposed who've had like 3 kids before or something, and they're like, I've been healthy through all of this. Prenatal care didn't do anything for me. I'm not going this time. I don't have time. But might have another healthy outcome, right? So there's different ways in which selection bias can happen when you're drawing a sample from your reference population. So you think about how this could happen in program evaluation. Your program participants might be different than the eligible people who don't participate, right? And they might be different on measured or unmeasured factors, okay? But in all of the examples, the assumption of a random sample from your target population to your sample is violated, right? So propensity score matching is a tool for approximating a randomized control trial and reducing the selection bias when we have these quasi-experimental program evaluations or in observational studies in general. It's not just for program evaluation, it can be used for observational studies, right? On average, what randomization does, so let's go back to RCT for a minute. If you randomize to the 2-year program or not, if you have the availability to do that, what are you doing? You're balancing your 2 groups across covariates, right? You're expecting them to be similar other than the program. And that's what propensity score is trying to do. Propensity score matching is trying to do as well, but without that randomization process. So on average, individuals with the same propensity scores, and we'll talk about what that is, are going to be are similar on the set of covariates that goes into that propensity score. So we're trying to balance the exposed with the unexposed group, trying to get an equivalent comparison group. And so just to introduce what propensity scores actually are, they're the predicted probabilities from a regression model where the exposure now becomes your dependent variable, your outcome variable. So the exposure in this case could be your program, right? So you got into the program, yes, coded 1. You didn't get into the program, no, coded 0. And then on the right side of the equation are all of your observed confounders. So every potential confounder you have between your exposure and your outcome, the outcome we don't see in this equation yet, right? When we're generating the propensity scores, our exposure is our dependent variable. Our ultimate health outcome or outcome of our program is not in this equation yet. But we do have all of those covariates that would confound that relationship between the exposure and our ultimate outcome. Okay? And so what that generates, if you have the predicted probabilities, you remember from Deb's lecture yesterday, the predicted probabilities, right, are you take your regression equation. So maybe now we have here is the exposure is a home visiting program, and that's your outcome variable in this model, right? And you have a set of, age, education, race, ethnicity, etc., right? As many factors as you can that might confound the relationship between home visiting and whatever your outcome is for your program that you want to study, right? And then you have your regression coefficients for each of these factors, right? You exponentiate those. The intercept plus beta 1 plus times x1 plus beta 2 times x2, etc. That's your predicted probability, right? It's the measure of occurrence. So if this is from a log binomial regression model, this is the probability of you having the outcome if you have that set of covariates, right? You would plug in for each x what that woman's actual value is. For somebody who's a teen, we might have dummy variables for age, right? If they're a teen, if they're African American, you plug in the x's for all of those, add up the betas, include the intercept, and then you have the probability of them being in the program, right? So that's what that predicted probability is. The probability of them being in the program given these characteristics, okay? And I'll show you an example of what those look like in a minute. So just if in the SAS world, you should, this might be a logistic regression model. Your model, you have your class statement to create your dummy variables. Exposure equals that pool of observed confounders and the covariates. And then now you have this output statement, out equals pred values. And that actually tells SAS to create an output data set called pred values, where P, which is the predicted probability, this is a SAS term, you see it's highlighted in blue, equals prop score. I just called it prop score. That's my name for it. So now I have an output data set with the propensity score in it from this equation. And I'll go through examples if that isn't clear now. But I still want to, so now that you're kind of grounded in what a propensity score is, I want to talk a little more still conceptually before we go into the actual methods. So in theory, all of the confounders between the exposure and the outcome should be included on that right side of the model to generate the propensity score. So all of those model selection techniques we talked about yesterday don't apply in this situation. Here we want to get the best model, the best predictive model of being in the program. So I don't care if something is not significant in your particular data set. If it is conceptually a confounder, a potential confounder between the exposure and the outcome, you want to include it. Here we're not looking for parsimony. We're looking for getting the best explanation. What are the factors that predict getting in the program? Okay? And that might include interaction terms, polynomials. There's a process of fitting this model to try to get the best, actually your outcome here is going to be balance between your two groups, between your exposed and your unexposed group. Okay? That should become clearer.
And so, could you give it, so what, in comparison to what we were talking about yesterday, what would you, on the other side of things, what would you be so concerned about with building your model?
So the question is, what wouldn't you be as concerned about if you're building your model? You wouldn't be concerned about parsimony, right? So especially yesterday when we were dealing with such a small sample size, we didn't quite finish, but we were trying to get, a model where there weren't too many extra additional factors in the model, because we lose precision then in the estimates of interest, right? So here we're not concerned about precision. We're not even going to use standard errors or confidence intervals out of this equation. We are just getting that predicted probability. So we want, because there's sometimes betas that have non-zero values but are not significant. So they can contribute to this propensity score even if they're not significantly related to exposure. If we conceptually think that they might be affecting exposure in intervention, program participation, and that relationship with the outcome, then we want to include them. Okay? So like I said before, confounders should be based on theory or prior empirical findings. Don't use model selection procedures. But remember causal pathway issues. So if you're, the definition of a confounder is that it's not in the causal pathway between the program and the outcome. So we want to make sure not to include those potential mediators between the program participation and the outcome in that propensity score model. So here's where I talk about higher order terms like polynomials or interaction terms. And this tip here is that before you model to generate your propensity scores, you should get rid of everybody who has a missing value on your ultimate outcome. And I learned this through mistake of my own. Because if you then, we're going to go to matching on that propensity score, but then if they're going to drop out of your final analysis for the outcome, you don't want them in this part either. So that was just a tip I learned from my own work. And you could consider, if you have, the one drawback to including a lot in this model is that you may have cumulative missing data. Every time there's missing data on one of the variables in your propensity score model, somebody's going to drop out and not get a propensity score, right? So you could use some multiple imputation methods. I'm not going to talk about that here, but you should maybe consider that as a way to preserve sample size and representativeness of your data. Okay, so just to give you an example of what the propensity scores look like. This is a fake data set. This is just a subset of the data. And you see the exposed yes and exposed no. So if you think of exposure as your program, those who said exposed yes got the program. And their propensity to get the program based on all of those predicted factors are closer to 1, right? And that's what we would expect. If you have a program that serves mostly low-income women, and you have a series of factors that predicts, and that kind of captures that low-incomeness, on several different measures, right? Their propensity to actually have participated in the program is going to be higher. So this is the idea here, right? And so you see the exposed no is lower, except there's exceptions, right? So this person may have been eligible for the program, but you didn't get them. But the propensity score is kind of a summary measure of all of those covariates, kind of a global representation of the woman. Okay? And so I'm going to talk a little bit about common support. I have a figure for that in a couple slides. But we want to make sure there's an overlap in those distribution of propensity scores, or else we don't really have a valid comparison group, right? If we don't have people in our program, if we don't have a comparison group that has people that will be representative of our program population, then it's not valid, right? So we have to look for this common support before we carry out the analysis. And that's something that we often don't do. With the typical multivariable regression models that we did yesterday, we don't usually take that step, right? We could be kind of comparing apples and oranges in our regression models and not know it. And that'll become clearer with a figure. But there's a balance here, though, between loss of sample size and loss of external validity when we go to match. And that'll become clearer in another slide. I'm sorry, I think I missed a slide. I just want to go back to make sure I made this point. Here it is. I'm sorry, I missed this earlier, but I did say that propensity score matching is a tool for approximating a randomized trial and reducing selection bias. And then on average, the randomization balances the characteristics across the group. But I wanted to talk about this idea of the counterfactual. How many of you are familiar with the concept of the counterfactual? A few, okay. So this is something that we are always doing and don't often put a name on it. In Epi, what are we trying to do? We're trying to, when we're comparing exposed and unexposed, if we're using regression methods, or if we're using propensity score matching, what we're trying to do is study, what the ultimate study would be to study a sample under one condition and then study them again for the same time frame under a completely different condition. So the first time around they're exposed, the second time around they're not exposed. They're exactly the same people, it's the same time frame. You know, it's like, what if that would have happened? What if they would have been unexposed? You want to compare them to themselves, exposed versus unexposed. That's the ideal study, right? No confounding, no nothing. It's impossible to do because it's counterfactual to what actually really happened, right? It took me a while to understand what counterfactuals meant. I thought it was some like highbrow epi term and that, but it really makes sense when you think about it. Anybody see the movie Sliding Doors? It's kind of an older movie. Love that movie with Gwyneth Paltrow in it. So the whole concept of the movie is that you see her going through two different paths in life, side by side, and you don't know which one really happened, right? You get really invested in one or the other, and you find out at the end which one was real, but the other was the counterfactual. This is what would have happened under different circumstances. So in all of our study designs, that's what we're trying to do, is get the best comparison group to estimate the counterfactual. What would have happened under non-exposure, right? So that's what we're trying to do in propensity score matching. We're trying to find, for each woman who participated in the program, we're trying to find her counterfactual, like who didn't get the program but had the same characteristics as her. Does that make sense? And that's what we're doing in regression modeling too. We just never say it that way, right? When we're comparing exposed to unexposed, controlling for a bunch of conditions, we're saying regardless of these conditions, we're trying to get that causal effect, right? Minimizing all of the possible bias. So that's why I want to go back to that slide to kind of root us in that. So here's a picture of what propensity scores might look like. I showed you what the values might be. But if here's your exposed, yes, they're in the program. They have higher propensity to be in the program. It makes sense, right? If there's characteristics that are associated with getting the program, then their propensity score, and this is their probability of being in the program based on all of those other characteristics, right? If they didn't get the program, you can see that the propensity scores are more evenly distributed across this distribution. And here's from the literature. This is just a really another way of showing it, just with a theoretical kind of example here. But when I talked about common support before, this is what I'm talking about. This is the area of common support here, where you have, if these are the exposed subjects, these are the unexposed subjects. So here's your program participants. They have a higher propensity of being in the program, right? There's this section over here where you have nobody who didn't get the program with propensity scores that high, right? And there's a section over here where there's nobody who got the program with propensity scores that low. So if we're estimating the counterfactual, we're trying to get the most representative comparison group. We don't have anybody to compare these non-participants to or anybody to compare these participants to, right? So our area of common support is where we have people that have similar propensities of being in the program. Does this make sense? And do you see how this is a way to deal with, but potentially deal with selection bias, at least address it a bit, okay? What we're doing in regression modeling, we're not ever looking at this, right? You can run a regression model with this whole sample, exposed versus unexposed, and not even realize how uncomparable your groups are, or how you're missing, you don't have a comparison for the either end. You'll still get model results, you'll still get beta coefficients, it'll be extrapolating beyond the data because you don't have a comparison group here. So it's interesting to think about this as a way to be a little bit maybe more rigorous in those methods. Okay. So once you generate your propensity scores and assess for common support, the propensity scores might be used in 4 ways. So some people generate a propensity score and then just control for it in the model. So if you have a small sample size, maybe like yesterday, when we did have a small sample size, maybe we could have generated a propensity score for having family-centered care, right? And controlled for that propensity score in the model instead of all those other covariates like race and age and everything like that. It's one possibility. Another possibility is to stratify. So like for the lowest quintile of propensity scores, the next quintile, the next quintile, and do separate analyses for each of those and then get a summary estimate, just like we would in stratified methods. You can also weight based on the propensity score, and the weight becomes then, so then you run your analysis, but you weight it as the inverse, so just take 1 over the propensity score. This gets a little difficult with survey sample. I haven't quite figured out how to incorporate both weights, and I've talked to other statisticians about that. We're not really sure how that works. But anyway, 1 through 3 we're not going to talk about today because a lot of the literature says that propensity score matching is really the kind of most rigorous one. So that's what we're going to talk about today, is actually matching one program participant to a non-participant based on their propensity score. Okay? And because this one is really the one that's most true to the issue of common support, because you can only match somebody that you have a match for, right? Yes?
So you mentioned sample size, and what would be too small? Like, is there an ideal threshold that you like to do this?
No. You don't necessarily need large sample size to do propensity score matching. I'm sorry, I was unclear about that. It's since we had small sample size yesterday, we could have preserve some power by just controlling for the propensity score rather than all the dummy variables for race, all the dummy variables for age and different things like that. The only thing I would say is that if your exposure is rare, so if maybe you do incorporate your program data into params or something like that. You ask a woman whether she participated in home visiting or not. If you have such a small number then ending up in your sample that actually participate in the program and you have a rare exposure, then this does get tricky. Because if you think about this, if you want to put as many variables as you can in this model to predict the exposure, if you have a small sample of exposed, then that model is going to be problematic. So that's where sample size does fit in. It actually is beneficial if you think about it, though, if your outcome is rare, because you're handling all the covariates in this model. And we'll talk about that more later after we've gone through all the methods. So does that help? Okay. Another question?
After you determine your area of common support, do you ever exclude those above and those below?
Well, as we'll see with matching, that automatically kind of happens. With the other methods, you can, if you're going to just control for the propensity score as a covariate, you can take that extra step to exclude those that don't have common support to be more true. So that's a good question. So we're going to go on with matching now. So we already talked about this multi-step process. The first step we already talked about, where you generate the propensity score. Then you use a matching procedure. So there's a lot of options for that, and I'm going to post some code on the website after the course for doing this. And there's a few different specifications you have to make on that matching. And then you're going to check the covariate balance, because that's what we're really trying to achieve, are equal groups, right? So if you see a randomized control trial, your table 1, you always see, right, is the characteristics for the ones who are randomized to the program and randomized to the control, right? That's the same thing we're trying to achieve here. We want to have a balance on those covariates. We want them to be exactly the same. And then this is your final outcome model then. So if your outcome is birth outcomes, this is birth outcomes equals your program. And now your individuals are matched on propensity score, but this is a very simple model because you took care of all of that control for covariates in that and matching by propensity score. Okay? We'll go through each of those steps. So there's several matching techniques available and that can be used alone or in combination. So nearest neighbor is exactly how it sounds. It's like you take one person who got the program, look at what their propensity score was, and find the nearest propensity score to them of those who did not get the program, right? Pretty simple, but it gets complicated when you're thinking in multidimensional space. You have multiple participants, right? So sort order actually matters in your data set. As usually you want to randomly sort your data before you do this, because the matching algorithms usually go through one observation by each. So you don't want the sort order of your data set to somehow bias that matching process.
I'm sorry, this might be tricky.
No, that's okay.
The score itself, that comes from the covariates, and how is that calculated?
It's remember yesterday, Deb talked about the measures of effect would be like your numerator. I'm sorry, the question was how the scores are calculated. So yesterday Deb talked about the ratio measures, how you calculate those from the model, but then also how you calculate like a probability of the outcome, right? So it's calculated from the beta coefficients from that model predicting the exposure.
So it's going to be 0 to 1 still?
It'll be on it'll be on a scale from 0 to 1. And so what's interesting is that we typically use a logistic model for that because it really doesn't matter. We're not estimating ratio measures. So we don't care that it's an odds instead of a proportion because it's all, we don't care for the propensity score. But if you use a log binomial model, remember there's one of the limitations of log binomials that sometimes you fit values outside of the 0 to 1, and that does happen. So usually the logistic model is just safer for generating propensity scores, okay? So nearest neighbor happens in the way I just said. You can do nearest neighbor within a caliper, and all caliper means is it's a width. It's like how far away will we accept a match? So if you have a propensity score of 0.7822 for your program participant, how far away are we going to accept a match for your comparison group? And 0.02 is kind of conventionally used, so a 2% difference above or below that, so like a 0.76 to 0.80, right? You would accept that as a match. But that caliper width, it's a balance between improving the number of matches you get and improving how comparable they are. Because the narrower it is, you may not be able to match your whole data set, or you're usually not able to match your whole data set anyway, but you might match only a small proportion of your data set. But if you widen it too much, you might have residual confounding. Okay, so that's kind of the balance. I have used 0.02 just because a lot of the statisticians that publish on this say that that's like a pretty safe estimate based on simulation studies and everything like that, but it's going to depend on your data and that too, because 0.02 might leave you with 50% of your program participants unmatched. Okay? And that's what I was just saying here. Kernel and local linear, I'm still learning about. They're more complicated matching techniques. I can't explain them right now. I just have to, I'll tell you they're there, and I still have not gotten to my understanding at that level. So there's a couple different matching techniques. I'll talk about greedy a little bit in the context of an example later. There's also, this is a newer macro I've found where you can adjust the caliper width. It does nearest neighbor matching in SAS. And so this is stuff that I will post for you post-training. And then the PSMatch, if you're a Stata user, PSMatch 2 is pretty flexible as well in terms of determining caliper width and defining how you want to set up those things. Okay, so this is greedy. We'll talk about that later. And then after you mesh, you want to check the covariate balance, because the whole point of doing this, right, was to make sure they're similar groups. So you're going to go ahead and do that. And now, we don't typically use it. I've seen people do this, but it's not recommended to use statistical testing for that process of comparing your program participants to your comparison group. Why might that not be a good idea to use statistical testing? Sample size affects your results so much, right? So if we're looking at covariate balance, it's recommended that you use standardized differences instead of significance testing. And these are actually really easy to calculate. You're basically standardizing for about a 10% difference above or below. And that's kind of by convention. Of course, if you want to be more rigorous and more rigorous, you could set that to a lower value, but again, you might have to go back to that propensity score model again and tweak it to make sure that that'll work. And so if not balanced, like I said, you respecify the model. So here's how you calculate standardized differences. It's very similar to like a z-score. It's basically just the difference in if you have, if your covariate is, so if it's child age or something like that, if you're looking at a program for children, you're treating it as a continuous variable. It's just the mean of that program group minus the mean of your control group over the standard deviation squared, the sum of the standard deviation squared for both of those over 2, the square root of that. If you are doing proportions, which we more often are doing, what's the percent African American in your program group and your comparison group? Here's the equation for proportions. pretty straightforward. If you throw this into a formula in Excel, you can do it for all of your, all of your comparisons pretty quickly. And then you can also calculate the percent bias reduction, because usually what we do is calculate standardized differences first on the entire sample before matching so that we can see the difference before and after, and I'll show you an example of that. And then you can calculate what percent of the selection bias you're reducing on that factor, right? Yep?
So, if you go back to the slide, the percent bias reduction, is that if you do a model twice, two different ways, or?
No, the unmatched is actually going to be comparing the covariate, so comparing the racial ethnic distribution in the program participants to everybody else in your potential pool of your comparison group. I think it's going to become a lot more clear with the example, so I'll show you the example here. So this is before I did any matching. So, so say I have an exposed group. I have a data source that has my outcome for both program participants and non-participants. So say this is vital statistics. I have birth outcomes for program participants, non-program participants. And we're going to have an example where you could do a linkage, right, of your program participant data to their birth records. And then you can identify participants and non-participants, generate a propensity score, right? But this is before the propensity score. You have everybody exposed to your program. This is clearly not vitals because the ends aren't right, but everybody not exposed to your program, that would be a much larger number, right? And then you have the difference in the estimates between them. And these are, these are expressed as means, just because this was, I realize I have to update this slide because I've figured out since how to do the standardized differences for proportions that I showed you on the last slide. So I had done this for using the equation for means, but that violates some assumptions because these are categorical variables. So, but this would be 38%, right? So if this is it is actually a child health survey. So it definitely is not vitals. Age 0 to 5, 6 to 11, 12 to 17, right? 38% of my sample was 0 to 5, 31%, 12 to 17, right? So this is the comparison group, the potential pool of comparison group. And you can see how they're different. And the absolute standardized difference shows that. That's the percent by which the difference in the means on a standardized scale, right? So then after the match, you can see how this goes down to 0.04, 0.11. These are almost equivalent then. So that's the idea. But now you see you have exposed 482, not exposed 482. So you remember in the last slide, there were 524 program participants. So here you've lost some people in the matching process, right? And now you have equivalent sized, it's 1-to-1 matching here, okay? So what you want is to see, you're probably going to see here that the covariates aren't balanced, and that what you want to see after matching is that they are. And we'll have a couple more examples of that. And this is what, if you run the propensity score model, that's run on the entire data set that you have available, right? And so here are your program participants. We've seen this before, right? And your non-program participants, less propensity to be in the program. After matching, by design, because you're matching on these, right? These are going to be just about exactly the same, the propensity score distributions. But that's not enough to check because this is like a summary measure across all those covariates. We want to check each individual covariate as well, like I did in the last slide. Okay? So, we're losing a bunch of these participants here, right? We don't think that they're comparable. Okay. So once you've established balance, then when you calculate the measure of association for the effect of your program on your outcome, you have to account for the fact that the data are matched. And then you can calculate your ratio measure or your difference measure, your relative and your absolute measures for the effect of the program. And it's a very simple calculation. Then you just have to account for the fact that now your matched exposed to unexposed are not independent anymore because you've matched them on similar covariate mix. So that's just you account for that in the standard error. And I have equations to do that, or you can do that in software, but it's really simple at this point because you just have a crude analysis, really. You don't necessarily have to. I'll show you. You can do it one way or another. You don't necessarily have to run another regression for the outcome exposure relationship at that point. You can just do a 2x2 table and use the calculations I'm going to give you. So I wanted one point of clarification here because it took me a long time to figure this out. A lot of the propensity score literature comes more from the economics world. And this cross-discipline issue. I love sharing methods across disciplines, but everybody calls something different. And it takes me forever usually to kind of weed through and figure out what do we call this, right? So a lot of the propensity score literature calls this estimate from this final model the average treatment effect in the treated. Took me forever to figure out what that means, the ATT. What the ATT is, it's the risk difference, or the attributable risk that we learned about in previous lectures. It's the same thing. And the reason why it's the average treatment effect in the treated is because you have, remember the counterfactual? Now you have chosen a group of people in the matching. You've chosen the program participants and the program participants not in the program. Do you know what I mean? So we tried to get the exact same covariate balance for the program participants for the non-participants. So now the effect of the program is only among that group. So among those who were likely to get in the program, what's the effect of the program? So there's some loss of generalizability there. Think about it in terms of risk difference, attributable risk versus population attributable fraction, right? This is just the effect of the treatment in the treated. And you do have a comparison group of untreated, but they're so similar to the treated group that that's who we think the treatment effect will work among. We don't know anything about what the treatment effect will do for those people who fell outside common support, right? And I think we don't think about that. Even though when we're doing regression modeling, that's what we're doing. Sometimes we're comparing apples to oranges. And sometimes you'll see the ATT ratio, which is just the relative measure then. But it took me a while to really understand that term, but that's how the economists think about it. Okay, so I talked about this accounting for the match design and the standard error. This is different. Is anybody familiar with conditional logistic regression to deal with a matched case control study? Right, this is a little bit different because when you're matching on case and control status, you're inducing selection bias because you're making sure the controls are just like the cases and the cases are the ones who have the disease. This time we're matching on exposure. So we don't have to handle the undoing of that selection bias. If you don't get this part, it's okay. I just wanted to explain it for those of you who know conditional logistic regression. We don't really have to do that part. The adjustment for the matching is only in the standard error part of the equation. So this is, I'm going to show you a way to calculate all of the measures using a 2x2 table, or you can use generalized estimating equations in SAS, and I'll show you that too, or in Stata. So here the setup of the 2x2 table is a little bit different though. To appropriately calculate the standard error, now your 2x2 table is an exposed cases, exposed controls, or exposed with the outcome, exposed without the outcome, et cetera, like we normally think about. This is a matched 2x2 table, where these are the number of pairs, number of matched pairs in each cell. Like in the A cell, it's a number of matched pairs where the unexposed experience the outcome and the exposed experience the outcome. Right? So you're going to have a matched pair where they got the matched pair where the program participant had a low birth weight infant, the non-program participant had a low birth weight infant. The real interesting information is in the discordant ones, right? Where you had either somebody who didn't get the program did not have, sorry, I always get myself confused on these two. The unexposed experiences the outcome, no, and the exposed experiences the outcome. So here's a program where the effect, if you have a lot of pairs in this box, that's not a good thing, right? Then your program is increasing the outcome. In the C cell is where you want to be. If your program's working, you have a ton of matched pairs in here, right? Because the unexposed experiences the outcome. Oh, am I getting this right? I'm sorry. These matched 2x2 tables. The unexposed experiences the outcome, yes. B is where you want to be, sorry, right? But if there's more matched pairs in B, I'm sorry, your program's working. If there's more matched pairs in C than your program is not. No. I was right the first time, wasn't I? I have to stop doubting myself. Let me start over. I was right the first time. The unexposed experiences the outcome, yes. And the exposed experiences the outcome, no. Here, exposure is the good thing, right? It's a program participation, so we want to be in this cell. I apologize for going back and forth on that. I hope I didn't confuse you too much. Questions?
Do people ever use a ratio other than 1-to-1, or does that make it just harder to find people with close enough propensity?
Yeah, I don't see people do much more than 1-to-1 matching. Because it does get difficult to find, a comparison person.
Would it actually make it, if there's more variability between three people matched, if it's a 1-to-2, would that make it so it controls for less bias, or?
No, I don't think. The only thing you might gain is some power. You might gain some power to really detect the effect if you increase the number of non-participants to your program participants. But it does become hard to find appropriate matches. So typically, most of it's done in 1-to-1 matching. But you're right that this particular table would not apply for one-to-many matching. You would need to use the regression approaches for that then. Yeah, another question, Molly?
I was going to say, does it depend on what your outcome is? Because technically both of those could be right. So if
good point. Yeah,
yeah,
I think
if your
that's
outcome is prenatal care, then you want it to
Right.
be yes, and if it's low birth weight, then you want it to be no. So I mean, both actually work
Exactly.
depending on your example.
Yeah, good point. Outside of an example, this was kind of difficult. If you have an adverse outcome,
Yep.
right, B is where you want to be. But if you have a positive outcome, right, if you've, through your home visiting program, you've improved maternal and infant bonding or something like that, you want to be in C. So I'm sorry, I didn't clarify. That's probably why I got so mixed up. Thank you, Molly. Okay. All right, so then here are the equations that go with that, because then you would have an estimate above the null or under the null, depending on what you would want. And so the computations here, based on that 2x2 table. So as long as you can organize your matched pairs into those 2x2 tables, which is pretty easy, you can calculate the relative risk this way and the risk difference this way. And the standard errors are pretty easy to calculate. They're all based on the cells. And you can get 95% confidence intervals. So there you don't even have to deal with software if you don't want to at that point. I did provide some code how to rearrange your data into the matched 2x2 table and then let SAS do the work for you. Yes?
I'm just looking at the relative risk calculation, and since I'm looking at this in the same way that I would look at a case control study, for case control studies, we'd only calculate an odds ratio. So I'm wondering how propensity score changes the ability to calculate the relative risk as opposed to an odds ratio based on the design.
We're matching on exposure,
Okay.
and really a relative risk is more appropriate, right? Because if you're looking at the causal effect of a program, your exposure is before your outcome. As Pat said, you have to make sure of that in your design, right? In order to say that it's a causal effect of your program improving an outcome. So that's why we're calculating relative risk here instead of an odds ratio. And because we don't have a matched case control, it's not a case control study, we don't have to report an odds ratio, we can report a relative risk here. Does that make sense? Okay. All right, so there's some handy code to rearrange your data. Here's a 2x2 table that I got SAS to spit out, and then I just did the calculations by hand. We'll go through more examples. You could also, like I said, use GEE. So all GEE is that you're running a ProcGen mod, a log binomial model from yesterday. And then you add this repeated statement here and this variable, the match2 variable, is your matching. You have to have a matched pair ID, and most of the matching algorithms will create that for you. So if you have this actually is on the long version of the data set where you have a program participant and their matched non-program participant as different observations in your data set, and you have a matching ID that matches them together, and you use that matching ID here and use this is for the covariance structure, independent. And what that'll do will just correct for the standard error because you have matched pairs, okay? So you could have done this by plugging and chugging and computing the standard error there, or using generalized estimating equations. Both will give you the same result, okay? Because this is just a crude model at this point, right? We're not controlling for any covariates because that's already done in the matching process. Okay, any questions before we get to an example? And I check my time. Questions? Okay, let's go through an example. Hopefully it'll make it a little more concrete. My first example comes from some technical assistance work I did. A lot of figuring these methods out. We're in partnership with Sarah Tran from Multnomah County Health Department. Who's here from Multnomah County? Somebody is, maybe in the other room right now. Yep. Oh, she was at Oregon too? At the State Health Department too?
Yeah, Multnomah County is the biggest county in Oregon.
Right. Right, yeah. So I worked with her on this project. So this is an example where I was kind of providing TA, didn't have my hands on the data. The second example is me actually doing the data, and it's really interesting. And it's like a progression of understanding the methods better. So I wanted to show you this because it is a program evaluation example. And I want to give total credit to Sarah. She did all these analyses. She's amazing. And I thank her for sharing these slides with me. So she did, I don't know if any of you, at MCHB, she did a presentation on this. She actually won an award for her abstract for this work. So that was at the conference 2 years ago. So she wanted to look at home visitation in Multnomah County. So they had, I'm not going to go too much into the program. Of course, that would be important for program evaluation, but I'm going to focus on the methods here. They had a home visiting program where they had several different ways that you could get into the different home visiting programs. So the eligibility criteria were different. So for nurse-family partnership, it had to be your first pregnancy or less than 28 weeks gestation getting in. The Healthy Birth Initiative really targeted Black or African American women. If you weren't eligible for one of these other two programs, but you were in a priority population, so low-income, teen, medical risks, homeless, then you went into this kind of more general field type home visiting. So she wanted to look at it as a whole, home visiting as a whole, and for one of the goals, which was improving pregnancy and birth outcomes. And what I want to point out here is that you have to remember with a program evaluation, when you have a external comparison group, right, you need to make sure that you have your outcome measured and measured in the same way for that external comparison group as you do for your program group. This is one of the trickiest parts about outcome evaluation, right? I mean, I'm sure I'm stating the obvious for you. You all know that, but this is why maybe the focus of her analysis wasn't on promoting family bonding and parent-child attachment, because where's she going to get that data for her comparison group that didn't get home visiting? They may be monitoring that as part of home visiting, but they only have that data on that outcome for home visiting participants, right? So she was using birth records here. Her research questions is what are the effect of the Multnomah County Health Department's home visiting program on pregnancy outcomes? And the second question was a methods question. So she wanted to compare, okay, if I do this propensity score matching, will it be different than my regular traditional multivariable regression approaches? One other thing I wanted to point out, if you look at kind of these priority criteria, what's interesting here is that there's a lot of different priority criteria. And it's not like you can just say, okay, women under this percent of the poverty level were eligible, and then pick everybody who didn't get the program as a match there. There was an interesting mix who were eligible for the program. So propensity score matching is kind of nice here, because on the variables you have, you can try to balance across some of those factors that influence selection. So she did a record linkage. There were 17,712 singleton births in Multnomah County from 2008 to 2009. She matched to the program data for home visiting and got 1,743 matched to birth records. And these were women who had one or more visits during the 10 months before giving birth. So she had to come up with, this is a whole thing about linkage, she had to come up with an algorithm about the timing of home visiting versus the timing of the birth to try to capture whether the woman was exposed to home visiting during that pregnancy. Okay, so then of that pool, she was able to match 97.1% of those to somebody else in this blue space who was similar to the program participant, right? So she got about a 97% match rate with the propensity score matching. So she built a logistic regression model. So here are all her covariates, and they're all, so what you're limited to is what's on the birth record. The same thing about the outcome, right? All of these covariates you have to get from a common source of data. This is the trickiest part about outcome evaluation, right? You need the same variables measured in your external control group as your program group. So think about that when you're designing your outcome evaluation for the exercise and for other evaluations too. And then she used the greedy 5-to-1 matching without replacement. I skipped over a great slide that explains that, so I'm not going to talk about that today. But it was a way to match basically within different caliper widths to try to improve the number of matches she got. She checked the balance diagnostics, comparing the baseline characteristics of the group, and then estimated the effects of home visiting. Her specific outcomes that she looked at were adequate prenatal care, small for gestational age and preterm delivery, and she used GEE. And then she compared the results. She did it with a traditional regression model too, and then compared the results. So we'll go through and see what she saw. So here are her propensity scores. So this is interesting. You have the entire birth cohort for 2 years in Multnomah County, the 17,000 births, right? This isn't the entire. This is the ones who did not get home visiting, who did not match to the program data, right? So you can see their propensity scores. A lot of them are right at 0 because they are probably the higher income women in Oregon, probably higher income white women who would not have been eligible for any of the home visiting programs, right? So you notice they get a propensity score of 0. They had a 0 probability of being in the program. You can see the program participants, it's a little more evenly distributed. So you see, depending on the data and depending on how good those covariates are at predicting program participation, you'll get different distributions of this propensity score. Because we're limited to what we have on vital statistics here, you can see this is kind of flat. It doesn't really it looked like you would expect it to, or like those pretty pictures we had before where the program group is like that, right? But anyway, so now she's going to match the program participants to somebody. So the idea is to get somebody who has the same propensity score there. Now, what's convenient, the fact that there are 17,000 up here helps with matching, right? Because you have a lot of people to go with. So here are, if we try to do the balance diagnostics before matching, we have our 1,700 home visiting clients and the 17,000 who didn't get home visiting according to the record linkage, right? You can see how different the characteristics are, hugely different. You know, we would expect this. And the idea behind the matching is that this is I'll orient you a little bit to this. These are standardized differences on the y-axis. So remember the equation I showed you about how to calculate standardized differences? The open holes are before she did any matching. So comparing for that whole like 18,000 program participants and non-program participants. This is the difference between, the standardized difference between the program participants and non-program participants. So pretty high, and this is on mean age. This is on educational status. For some reason, the high school was very similar. Or on race, you can see how different they are. Now, after matching, you see all these blue dots. The idea by convention, remember how I said below the 0.1 line is usually good, and I have a reference for that. All these blue lines, after we've matched, we have covariate balance. So I could have showed it to you like this as well. I don't think she did show it that way, but it's a nice way to summarize in this chart to show that after we've matched, now we have the 16-something hundred pairs, and they're matched along all of these characteristics. Note that they must have been using the new version of the when did you, in Oregon, when did you implement the 2003 revision of the birth certificate? 2008, right? So she had WIC, which was helpful, right? Another explanatory variable, right? Oh, were we linking it though? Maybe they were linking. Maybe it was a record linkage. That's how they got WIC status. So they did a record linkage. And she had I can't remember what OHP is.
Oregon Health Plan or
Medicaid? Yeah, Medicaid. So they must have been doing some linkages to vital statistics to get these additional explanatory variables. The rest come off of the birth certificate. Okay, so here are the results, just plotted. And so this is the likelihood of home visiting women experiencing each outcome compared to like the matched non-home visiting women, and then by method of analysis. So here is the crude, and so here's where you see that, that the effect of home visiting lowered adequate prenatal care rate. So this is what we're trying to correct, right? Here's the selection bias. The women who participated in home visiting, of those 18,000 births or 17,000 births or whatever, the women who participated in home visiting had worse adequate prenatal care rates. Well, we expect that because we're comparing to higher income women where you have a completely inappropriate comparison group here. So here's the selection bias that we're trying to correct for. Okay? In the adjusted, this is just multivariable adjusted regression, a logistic regression. She got a non-significant increase, not even, basically at the null for adequate prenatal care between those in home visiting versus not. And then with the propensity score matching, she got a very similar estimate, right? For gestational age, you can see the home visiting participants were almost significantly more likely to have a small for gestational age baby. Again, there's the selection bias. With multivariable regression, she got 0.92, and propensity score matching 0.95. And then for preterm birth, here's the selection bias. Here it still looks with the adjusted methods that there might be some elevated risk of preterm birth for program participants. And here with the propensity score matching, it's slightly lower with confidence intervals spanning the null. So was there a benefit to doing propensity score matching here? We conclude basically the same thing, right? This is very problem dependent. You can't just say that propensity score matching is going to be better or worse than multivariable regression. It's very problem dependent. And so that's why I have another example too. So in this particular case, we didn't come up with really different conclusions. You can see here maybe we're accounting for selection bias a little bit better. Okay? But still, it still doesn't look, if the program was really working, right, we would expect it to be below the null and it would be significantly reducing the birth outcomes, right? So we're not really seeing an effect of home visiting here at all. She did go on to do some additional analyses. Was there any questions? I'm sorry, I might have missed. Okay. She went on to do some additional analysis to look at dose. So she did have the number of visits for home visiting participants, wanted to see whether those, remember her home visiting participant group was defined as those who got one or more visits. So there might have been women in there who got only one visit. So she looked at women who got 3 or more visits versus the comparison group, 4 or more visits, 5 or more visits, 7 or more visits, and seemed to see a little bit maybe of an effect on getting adequate prenatal care with the number of visits. Now, this is an association. Is there an issue with this potentially? I wouldn't take this to say that there's a causal effect on home visiting and getting adequate prenatal care. Why? This doesn't have anything to do with propensity score matching. I'm sorry, go ahead. No. This group of 3 or more is, you're just reducing the number each time. You're right. So these aren't mutually exclusive groups. But what's the other issue? Exactly. Right, so getting into home visiting, they might have been referred by their prenatal care provider, right? So there's lack of temporality here as much, right? So it might be the other way around. There might be reverse causality, right? That women getting adequate prenatal care had time to get into home visiting, right? And had time to have that many visits. So I wouldn't, this is association, not causal. But that's outside of propensity score matching. Now, I will say one thing that I think we've figured out since this analysis was done is that she just took the propensity scores from that original model, and I advised her to do this. This wasn't her fault. But propensity score for home visiting, yes, no. Took those propensity scores and just rematched for each of these groups. But this propensity represents the propensity to be in the program, not the propensity to get 3 visits, to get 4 visits. So those groups are probably different. So up to here, now we probably have less comparability between our 7 or more visit group versus our none. So she rematched but didn't reproduce propensity scores. And I've talked about this with several different statisticians, several different groups, and I think it might be best if you're doing subgroup analyses to re-estimate the propensity score. Because then your comparability for the contrast you're making should be better. Does that make sense? So she also did, looked at program effects, so think about effect modification. Maybe the program worked really well for African Americans, but that effect is diluted by looking at all program participants. So she looked at among African Americans, the matched pairs within African Americans, but without re-estimating the propensity score. I really think that these subgroup analyses, you should probably go back and re-estimate the propensity scores to make sure that you're getting a comparable group. First, restrict your data set to African Americans, generate a propensity for being in the program among African Americans, and then rematch. So that's the one thing I would have done differently, knowing more now.
I can have a question off of that.
Sure.
Kind of a similar thing with just regression. But like for our home visiting program, you have to be in Medicaid. So I just automatically reduced the population to Medicaid enrollees as my comparison group. Is there any disadvantage to doing propensity score? Like I know she used the entire birth population. Is there any disadvantage of doing just the Medicaid group to start out with, or?
I think it makes a lot of sense if you have clear eligibility criteria, I think it makes a ton of sense to first restrict, if you have data to restrict on that. So here the eligibility criteria, that's why I pointed that out, the eligibility criteria were kind of mixed. You could have been a teen at a higher income level in a priority population, so it was harder for her to exclude but if you have a program where there's clear either income eligibility or that, I totally recommend first restricting to those who would have even been eligible. But then the propensity score matching is to try to make the program participants more comparable to those who were eligible but did not participate.
Okay, thank you.
And so this question is around the subgroup. This is a way of looking at the subgroups using propensity score matching. If you were to approach it using multivariate regression, would you just look at the predictor, the betas for the first time? Like, would you just look at it for that?
No, you would actually restrict your sample to like African Americans, and then run the regression model among African Americans. So it's a subgroup. It's truly a subgroup analysis.
Okay. Thank you.
Right. It's not the beta for the African American would be the effect of being African American, not the subgroup of African Americans. Okay, so this is just my question. I think it might be better to regenerate those propensity scores and then rematch for the subgroup analyses. Okay. So some of the limitations of her study were the linking of program data with birth records is subject to misclassification bias. So it's not totally clear whether home visiting women might have been misclassified as non-home visiting women because she didn't find the linkage to the birth certificates for the program participant. The propensity score analysis, now huge, largest limitation of propensity score analysis. We're only balancing on observed covariates. How many factors go into non-program participation that we don't measure in birth records, right? We don't know if a woman's homeless or not on the birth record, right? Or has unstable housing. We don't know stressful life events. We don't know if she has daily emergencies that are preventing her from getting to the program. We can't measure any of that. So that's where a randomized control trial is supposed to balance on measured and unmeasured characteristics right through the randomization process. Now there's still issues with it though, because you might have differential follow-up depending on how far out your outcome is. A randomized control trial could be, you could totally throw off that comparability by having differential follow-up, to the outcome. So it's not perfect ever. But this is the disadvantage of propensity score matching compared to randomized control trials, that you can only balance on things you've measured on. You're not balanced on unmeasured confounders. And I think I may have mentioned this on Friday in the webinar, but people are starting to do more sensitivity analyses to try to figure out what is the potential impact of unmeasured confounding. And I'm working on trying to figure out those methods so I can incorporate those, because I think those are very useful. Like a confounder would have to be this strong to eliminate the effect we're seeing is kind of the message there. So I think we can, it's similar to kind of like Pat was saying earlier, ruling out all potential biases that may be influencing our results. Okay, but this is the huge limitation, is that it's only on measured confounding. And then we also didn't find a match for 3% of the home visiting women because they had the highest propensity scores. They were outside of common support. And so these are the women that probably had the worst birth outcomes too. So there may be, an issue there, but 3% is actually pretty decent if you think about, finding a match. So I just want to go through very quickly, and I might just cut to the chase on this. I did another analysis. This is one that I had my hands on that I can explain a little bit more of. It is not a program evaluation, though. I apologize. I don't have a lot of access to program data sitting at the university. So this empirical example is actually a more etiologic question. But if you can think of breastfeeding as your program, I know it's not a program, but breastfeeding should improve outcomes for kids, right? So breastfeeding here is my exposure, and my outcome is early child development. But I want to just point out a few things about the methods here through this example that are a little bit different than Sarah's. So I used the National Survey of Children's Health, the 2007. My inclusion-exclusion criteria. So we only have breastfeeding data on NSCH for 0 to 5-year-olds. So I'm only looking at 0 to 5-year-olds. And I had some other exclusion and inclusion criteria based on the outcome of child development. My exposure here is a dichotomy. I fought with this so much because I wanted to look at duration. And so I wanted to look at never breastfed, initiated, and different categories of duration, because in NSCH they do ask the two questions. Was your child ever breastfed or fed breast milk, and how old was the child when you stopped? And I think that's in weeks or months. They can report it either way. So we have a duration measure in NSCH. But because of the matching process, and I've even emailed a few statisticians about this, your outcome variable in the propensity score model is your exposure, right? Exposed, unexposed. We could run a generalized logit model. We learned how to do that yesterday, right? And get the propensity scores for those. But then when you get to the matching, I tried to do it, and it did not work. I could not match different categories to a comparison group, because then you dealt with replacement and that. I fought with it because I thought that I should be able to. So right now, with the matching methods, we're kind of restricted to a yes-no exposure, okay? Which is okay in program evaluation, unless you want to look at dose, as a whole, right? But for here, this is why this variable is not satisfactory. But the variable is 6 months or greater or still breastfeeding. So I call that extended breastfeeding, of breastfeeding 6 months or longer, or less than 6 months combined with a never breastfed. So really this is looking at the effect of extended breastfeeding. So I just wanted to point that out because it is another limitation. Now, what I was told by the statisticians is that you can do the propensity score weighting if you get propensity scores from a generalized logit model. But then I ran into the complex sample design weights and how do you incorporate both weights. So I think we're still working on that. So just to point out that right now, the methods I'm showing are just for a yes-no exposure, right? Okay. So my outcome here is one of these CAMI measures from the NSCH, and this is it's a parent report on several different development domains, behavioral, language, motor, et cetera. That they have an index for it, that you're high, moderate, or low or no risk for developmental delay. And this is actually, the parent's evaluation of developmental status is actually used clinically to screen. And it's pretty good from parent report because parents know their kids really well. So it is a parent report measure, but it's actually pretty predictive. It's been shown in different studies. So here's just the questions. I'm really going to fly through this. On the NSCH, we have a ton of covariates, right? So a little bit better maybe than vital statistics in terms of trying to balance our groups of those who breastfed and those who didn't, which we know are very different groups of women, right? Those who breastfed 6 months or longer especially versus those who did less, right? So we have all the child factors, maternal factors, family factors, and geographic factors. These are all of the factors that went into the right side of my model to predict breastfeeding to 6 months or longer. Okay, so I went through all the same steps as last time. Here I'm estimating odds ratios for the same reason I was estimating odds ratios yesterday with the complex sample data in SAS. We're restricted to survey logistic. I think we're breaking down some of those barriers, but you will be looking at odds ratios here. And just a little bit about remember I stressed the most important, these are your sample characteristics, your prevalence of the exposure. Very, very important to report all of this before you report any ratio measures. So you can see, so this is going to become an issue later. So 47% of the sample was breastfeeding greater than or equal to 6 months. Okay, so that's an N of 10,633. This is with the national file among 0 to 5-year-olds, right? Here are just my outcome prevalence estimates for the whole sample and the different domains that go into that outcome variable. So here I estimated the propensity scores, the propensity for breastfeeding greater than or equal to 6 months. Here's what they looked like for the entire sample. So now remember that what you don't see here is that this is almost half of the entire sample. So when I'm going to take these and try to find a match up here, I'm going to reduce my sample size, okay? So I matched each child breastfed 6 months or longer to a child that was breastfed less than 6 months or never on that propensity score. So I took, for each of these children in this distribution here, I took one child who had a similar propensity score. And I used nearest neighbor matching within a caliper with a 0.02, I think I mentioned before. And one-to-one ratio of exposed to unexposed. And I did it without replacement. Most statisticians I've talked to have said that matching with replacement is just goofy. I tried to do that, and I ended up with a couple sets of, this is a case where it's not one-to-one matching anymore. It's still one-to-one matching, but I had some non-breastfeeders that were matched to like 100 cases, 100 breastfeeders, right? So if you use replacement, you can use that, the non-program participants or the non-breastfeeders multiple times to match, and it's not right. They're overrepresented then in the data set, right? So I matched without replacement, but the effect of that on my sample size you will see. So I calculated the standardized differences before and after. You see this looks pretty familiar. This is interesting because here are the maternal characteristics. Unmatched, you can see there's a little bit of unbalance. The orange show after matching that I have more balance on these factors such as sex, race, ethnicity, age, birth order, birth weight. I think we're not seeing as much differences before matching as we would expect because of my unexposed group still has women who breastfed up to 6 months, remember? So maybe those two groups aren't as different as the initiators versus non-initiators that we're used to kind of seeing. But here you can see this was, I'm sorry, these were the child factors. This is why they're not that different. I'm sorry. These are the child, not the maternal factors. So you wouldn't expect the child factors to influence breastfeeding, right? The maternal factors were a bit more different before matching, right? And you would expect that, right? On age, education, marital status. And then here are the family and geographic factors. So you can see in the West there was quite an imbalance until we matched. Those who were breastfeeding versus not breastfeeding were probably because women in the West are more likely to breastfeed, I think, right? If you look at regions of the U.S. But then once we matched, you have the standardized differences under 0.1. And then I performed the matched analysis. So I just wanted to show you my matched 2x2 table because my outcome was 3 categories, remember? So here I did actually use generalized logit modeling to look at these different degrees of the outcome being high risk of developmental delay, moderate, or low risk. But what I did with those calculations is just created each 2x2 table, right? So now I'm comparing, these are the matched pairs for those who were breastfed less than 6 months or never and were high risk, and those who were breastfed greater than or equal to 6 months and were high risk. That's my A cell and my B cell, C and D. And then I did every combination of those because I have this 3-category outcome. It's just an extension of what you saw with the dichotomous outcome. But then it requires you to do the different 2x2 tables with low risk on the outcome being always kind of your common referent for the outcome variable, okay? But remember, it's matched pairs. Okay, so I used the equations and calculated a relative risk of 0.78, meaning that those children who were breastfed were 22%, had a 22% lower risk of high developmental delay. This is high versus low. with the confidence intervals from 0.68 to 0.88. So if you were thinking about this as being the effect of a program on a poor outcome, it would be in the same direction, right? Below the null, the program would improve the outcome, okay? The risk difference here is about a 2% difference with confidence intervals that are, very, very narrow given the sample size here in the matched estimates. Okay, so this is just showing the same thing in the 2x2 table, I think. And then I compared the analytic methods. I did it with multivariable modeling. So here are my results. So we have high versus lower, no risk of delay, and moderate versus low risk of delay. We have the two contrasts from the generalized logit from the 3-category outcome. We have the crude, the adjusted, or the propensity score match. So regardless of method here, it seems that extended breastfeeding doesn't have an effect on moderate risk of developmental delay. But those who breastfeed an extended amount of time seem to have a reduced risk of having a high risk of developmental delay. Okay. The crude, you can see, is really impressive because of selection bias of women who breastfeed 6 months or greater. You can see that these get closer to the null but are also pretty similar. What do you see here, though? The standard errors, the confidence intervals get much narrower. Does anybody know why that is? Okay, a matched analysis is much more efficient. Because you've narrowed the standard errors actually by matching. You've made them more similar, less variance between your matched pairs, right? So you get a much more precise estimate. So that's a difference here. The point estimates aren't different, but you get a much more efficient analysis. And then I looked at each domain separately, language, behavior. I didn't show all of this, but there were some cases where the multivariable and propensity score matched values were a bit more different than this, or that we saw in the Multnomah County example. But basically, we're not seeing many different results. You see maybe a more efficient analysis here. So let's talk about these things. So like I said, several of the outcomes that I didn't show here, the PS-matched results diverged, and I can post the entire slide set when I post it. I just, for time, only showed you one outcome here. The odds ratios from the PS-match estimates were generally farther from the null and had the narrower confidence intervals, meaning that we were seeing an effect of the program with propensity score matching that sometimes, or the effect of breastfeeding with propensity score matching on some of the outcomes that we weren't seeing with multivariable regression. But again, it's very problem specific, very data set specific. So the propensity score matching sets a high bar for group equivalence because of that common support issue. But then, remember, the findings apply only to the effect of the exposure on the exposed. And this is one of the main reasons I wanted to show this example, because when you're thinking about generalizability, you have your original sample here. Remember, there were 20,000 in my original sample, and then here's my match sample. I kind of skipped over this, but I only had 8,807 pairs. Remember, I had like 10,000 some exposed to extended breastfeeding? Well, at 20% of those I didn't match. Okay, I didn't find an appropriate match in the other group. So one thing I could have done was widen the caliper width to try to get more matches, but then I might have residual confounding. So you see where that balance is? So what's interesting is that I had a very comparable group in the extended versus non-extended breastfeeding group. But it was very different from my original sample. Because look at the original sample was much more likely to be African American and Hispanic, have greater than 3 kids. Yeah, this is birth order, so that's a similar thing. Be much more likely to be a teen, more likely to be less than high school, more likely to be under the poverty line, and less likely to be over 400%. So my findings are internally valid for the group that was likely to breastfeed for extended breastfeeding, or the group, if we want to think about it in terms of program evaluation, the group that was likely to get into the program. They're internally valid, but not externally valid to the population, because these don't represent, the group that we excluded due to non-comparability. Does that make sense? So you lack external generalizability when you do this propensity score matching, but you can get a program effect that is valid for the group that would have gotten the program. So here's one of, but that's what's happening in multivariable regression too, right? The same thing's happening, it's just more explicit here. So these were some of the study limitations. So it was actually 24% that I didn't match. I also did not do multiple imputations, so I lost some of the sample because of missing data, all those covariates I had. NSCH is great in terms of missing data. There aren't many, and they do impute income, right? So 5% actually isn't too bad, but I could have improved that with multiple imputation. But some of these are some methodological limitations, mostly due to what I was talking about having that dichotomous exposure that I didn't really want. But let's get into the discussion. So recall that counterfactual ideal that each individual could be studied both in the presence or absence of exposure. This becomes more explicit when you go through this process, right, that you're comparing apples to apples. It sets a high bar, and it yields more equivalent results groups for comparison if you do exclude those who are outside of common support, either by matching or explicitly doing that if you're going to use the propensity score in a different way. But the generalizability is then affected. It's only the average effect of the treatment among those who got treated, among those who had a high probability of being in the program, right? The multi-step process, whereas traditional multivariable regression, right, we just run one model. But you're also tempted, so one of the benefits is that in multivariable regression you can do some model building. You're tempted to, make the results look like you want them to. Not that we're ever trying to bias our data, but it's very explicit what the exposure-outcome relationship is. You can control for different factors and see how that changes. In this case, we're thinking theoretically, conceptually about confounders, handling them here before we ever look at the exposure-outcome relationship. So it's a little bit, it makes us be a little more rigorous and theoretical in thinking about what do we want to balance on, and make sure that we're balanced on all of those factors. And it makes sure that we're choosing covariates in our model from a conceptual standpoint rather than fitting a model and playing with different model building techniques to get maybe a result that's a little more favorable. This is all I'm saying. We're trying to mimic randomization through this. I think I hit all the main points about pros and cons. I already talked about a rare outcome. So I'll let you guys have, I know you don't have these slides in front of you, so this is probably driving you nuts that I'm flipping through these, but you can go back and kind of digest these later. I really do want to have at least a couple-minute conversation. What do you think? Do you think you might use these methods? Do you think there's a benefit to going through this process and doing this? Hopefully I've made it a little bit more straightforward and easy to go ahead and apply this process. It's really not that much more difficult once you have the tools. But it is a few more steps than a typical multivariable regression. So Molly, let's use the microphone.
I definitely think this is very valuable, and I definitely think that I will apply it in some work that we're doing in the near future. But my biggest worry, I know you compared to the population, how the population changed, so the generalizability is lacking. Mm-hmm. But what about the people that are excluded? I know you mentioned it a little bit that they might be the more high risk of the group with poor outcomes. Do you ever compare the outcomes of the matched group to the non-matched group to see if there's any type of bias occurring in the outcome too? I think you definitely can compare the outcomes for those who ended up matched versus non-matched, right? I only showed you the balance on the other characteristics, and you're likely to find poorer outcomes in the non-matched group because they're probably the hard-to-reach women that you can't get into your programs because they have a million other things, daily emergencies to deal with, right? So the question is, if the goal of the study is to look at the program efficacy, and get internal validity, is the program working among comparable groups of women, then to get the causal effect of the program, all you can do is compare to women who would have likely gotten the program but didn't, a comparison group. So it's almost like you have to address that other group separately. They have worse outcomes. We don't know how the program would affect them because we don't have anybody representing that group in our program. So you just think about it in a different way when you think about it that way, I think, Other comments or questions or thoughts about whether you'd use this or not? Did I break down any barriers to using this that maybe you've seen in the past? And this is the beauty of this training course. You remember that our time is not just here.
There's technical assistance too. And now, like when I was doing TA with Sarah, I was feeling very unsure of myself, trying to learn along the way. And again, I can point out things that I may have suggested differently now. I feel very much more comfortable in these methods now and would love to collaborate with you on something. So remember that, you know, you have my time, you have other faculty members' time after this, because an hour and a half probably is not enough to really digest this, but I'll put the tools up and I'm happy to help. Any other closing comments? Carol, please. I told you I would leave time for discussion and we'd hardly have any, I'm sorry.
And I tried this after I learned it from you, and I did get it to work. I mean, it made matches, and I don't know, I probably made some mistakes, but I printed out some of the cases that had matching propensity scores next to each other.
Okay, so
and they did not match in their predictor variables.
You know what? Right, I failed to say this. So what propensity score matching does is it matches on average in the population. I did not say, it was, I think it was written on the slides, I did not explicitly say that. Very good point, Carol. If you look at one match, you know, they might have very similar propensity scores. You might have a white teen matched to an African American 35-year-old. Right? So it's not that the individual matches are equivalent, but you don't care about that. It's on average. Remember, all of our, Deb said this yesterday, all of our regression methods are on average. What is the effect of the program in the exposed versus unexposed? So it doesn't matter that you don't have, you know, matching women. And this is one of the benefits of propensity score matching, is that if you tried to match on 15 factors like I had like in the NSCH, you wouldn't have enough, you would have even a less matching rate, right? So the propensity score averages that covariate mix out into one value that you can match on, and then it's on average for the sample, you have balance. You might not have, you know, exactly matched one woman to another, but that doesn't matter because in our methods we're looking at the average effect of the program. So I know that's not satisfying, but it should not matter. If you're looking, that's the whole idea of statistics, looking at a sample instead of looking at, you know, the one match pair. Great question. I didn't make that explicit. I hope that's more clear.